my name is Sanjay Vijendran, and today I'm going to talk to you about ESA's Europa Penetrator Development Program and the link to search for extraterrestrial life. The work I'm going to describe to you today has been done over many years with industrial contractors and institutes in the UK, led up by Airbus Defence and Space in Stevenage, with collaborations with University College London, Kinetic Space. I'm going to start by describing to you the what and why of penetrators. Penetrator is a projectile-shaped spacecraft that impacts the planetary surface at high velocity in order to embed itself into the surface. Well, why are we interested in penetrators? This is a completely new class of spacecraft. Well, for two reasons. They can fill a niche when only a small spacecraft is able to be delivered to a planetary body surface due to severe mass and cost constraints. And two, they provide direct access to subsurface material by virtue of tunneling into the surface during impact. In this way, when you're needing in a mission to get down and do scientific investigations below the surface, you almost get that for free during the impact process without having to embark a deep drill device. Penetrators have actually flown in space. Unfortunately, none of the missions have been successful. Only one actually reached its target, the NASA Deep Space 2 mission to the Red Planet. And the Russians have also flown a mission, the Mars 96, but that failed during launch. The Japanese took it to a Phase B with the Lunar A program, but unfortunately that was cancelled. And the Russians are now considering it for the Lunar Globe mission in the later part of this decade, which may fly the Japanese penetrators. We started our current ESA Penetrator development program in 2009 with a Phase 1 system feasibility study. We used as a reference design the ESA Laplace mission, which was being studied in Phase A at the time as part of the Cosmic Vision L1 program. And we consider the penetrator as a possible piggyback payload on this Laplace mission to Jupiter and Ganymede. However, during the Phase A study, Laplace soon showed that there was no mass margin available, and so our study targeted Europa instead, using the NASA Jupiter Europa Orbiter mission as the reference. Europa is a particularly challenging surface to send a lander or penetrator. There's a few reasons for this, and the first, it's airless, which means that all the braking would have to be done with chemical propulsion, as we cannot use parachutes to slow down. That results in a huge amount of fuel required in order to do this braking. Secondly, it's very cold. At 100 Kelvin, especially with a penetrator embedded and in direct contact with the ice, this really drives the thermal control of the system and the power and energy that's required in order to keep the penetrator systems warm for long enough to conduct the mission. The surface at 100 Kelvin is also extremely hard, and that means that the penetrator has to survive huge G loads, thousands and tens of thousands of Gs during the impact. It's also potentially very rough at the local scales of the penetrator, and this reduces risks of ricochet potentially of the penetrator during the impact process. There's also a large amount of radiation, although with the penetrator embedded deep into the ice, the ice itself forms a radiation shield, and it's more protected than a lander on the surface would be. But overall, it's a relatively poorly understood surface, especially due to the fact that there are no high-resolution images available of the European surface, with the best images coming from really old missions like Voyager. This is the mission concept we came up with, starting with a circular orbit around Europa at 200 kilometers altitude. We're detached from the orbiter, and then a small propulsive burn is done to reduce the orbit down to 32 kilometers, at which point, firing tangentially to the surface, the main braking burn is done such that we achieve essentially a stop and drop maneuver where all of the orbital velocity is cancelled out. 1.6 kilometers per second is brought to zero, and the penetrator then free falls from 32 kilometers, an altitude that's designed specifically to reach an impact velocity of 300 meters per second at the surface. An orientation maneuver down to the vertical is required during this free fall, as well as a spin-up process of the entire delivery system and penetrator before the penetrator is released just prior to impact, with the delivery system moved out of the way in order that it does not crash onto the landing site of the penetrator itself. The impact conditions to be achieved are 300 meters per second velocity, as well as an angle of attack of less than 8 degrees or so, and in order to reduce the side forces on the penetrator, which could result in severe damage to the internals of the penetrator itself. The penetration depth that was aimed to be achieved was somewhere between 1 and 5 meters, depending on the hardness of the ice. Here's what we came up with as a design for the penetrator and the delivery system. On the top left, you see the schematic of the penetrator itself. And one of the novel things that we came up with to ensure the thermal control was essentially a vacuum flask, thermos flask, a 2-layer penetrator, an outer shell, a vacuum inside, and an inner shell, which encompass the bays holding the scientific instruments and the subsystems to power and communicate. These inside bays were held off by some standoffs on the outer shell to ensure that the vacuum gap was maintained. The overall mass of the penetrator was 12 kilograms for a mass of half a kilogram of payload. But the delivery system, which was the part that would get the penetrator itself to where it needed to go in the right conditions, that turned out to be much larger than the penetrator itself, with the overall total penetrator plus delivery system coming up at about 62 kilograms. And this is something to bear in mind when thinking about penetrators, that is not just the part that carries the scientific instruments, the payload and things that impact into the surface that needs to be considered, but also the delivery system that gets the penetrator to where it needs to go. And it usually is the case that this delivery system is many factors larger in mass than the penetrator itself. So it's the entire system that needs to be considered to understand what the overall system impact is on a particular mission. We then moved on into a phase 2 study for 800 kilo euros and a duration of 18 months, trying to achieve a TRL of 4 to 5 for some of the components of the penetrator platform. The focus this time was an astrobiology for Europa, with a consideration also for Mars. And we use a bottom-up approach for the payload, rather than starting with an overall mass limit for the penetrator that we were trying to target. We set a limit of 4 kilograms for the payload. We designed the payload, and then we moved on to update the phase 1 penetrator design in order to support this new payload and see what was the overall penetrator delivery system, total system mass that would come out from that. After that, we then moved on to a small scale and then full scale breadboarding and testing of the shell and sample acquisition system. A bit about the science goals. Well, as I mentioned, astrobiology was the focus, and this resulted in a design which included a mass spectrometer, a habitability package, as well as an optical microscope as the 3 main key minimum set of instruments that would make an interesting astrobiology mission. In addition to that, in order to be able to obtain samples for the scientific investigations, we needed a sampling system that would go outside of the penetrator shell, sample some ice, and bring it back in to the scientific instruments. So this required a drill that would actually drill through the shell, collect material for analysis, and bring it back in. So here's a schematic of the forward compartment of the penetrator with the astrobiology payload. And you can see in blue here in the middle the sample imager, the microscope, looking at the samples inside a sample container. On the right, the largest instrument is the mass spectrometer. And on the top are the 2 drill systems, one pointing in each direction, which would be used to sample the ice into the instruments. Here's a drawing, a schematic showing the whole penetrator. And as you can see, you have an outer shell and you have two bays inside the penetrator. And these are two compartments that were also thermally separated from each other. And the idea of this was that the front compartment with the scientific payload was designated the cold bay. And by this we meant that there was no active heating involved, because the scientific investigations was thought to be able to be done in a short enough time such that the penetrator would not need to be heated before the investigations were done, the data was transferred, and then the instruments and systems in the front cold bay could be let to freeze, and it would be the end of the mission for that part of the penetrator. However, the rear compartment, or the warm compartment, that supported the batteries and the communication system and some other payload like a seismometer, which required longer term investigations, and that would be actually kept warm by battery energy for a longer period so that there was sufficient time for the data to then be relayed back to Earth via the orbiter. So there was a two-part penetrator concept that was developed in this phase 2, with a cold bay at the front with a short lifetime, only a few hours, and then a warm bay behind with a lifetime of up to 7 days. And the key thing, you can see in the yellow strips on the sides, at the bottom and the top, are what we call the snubbers, or the standoffs, and these This is the delivery system, and you can see how large this is, and its function was predominantly to deliver the penetrator to the right place at the right conditions. And so it provided attitude control, it timed the descent, provided the huge delta V that was required. So overall, the total mass budget we came up with was 20 kilograms for the penetrator itself, including 4 kilograms of payload. The delivery system came in at 125 kilograms, of which 65 kilograms was propellant, with a total penetrator, a system mass of 145 kilos. We then moved on to a phase of small-scale testing in order to inform what the survivability of some of the key components might be when it came to the full-scale tests. And for this, we used the gas gun at the Cavendish Laboratory in Cambridge, where we could fire 50mm projectiles down the gun up to velocities of 1200 meters per second, but we were only looking at velocities up to 300 meters. We carried out a number of tests at the small scale to look at the survivability of batteries and data loggers that we would need to measure the accelerations in the full-scale test, as well as the key components to provide the standoffs for the vacuum system, which was the Torlon leaf springs, and also the drill components and some critical UHF communication system components were also tested. After successful small-scale testing, we moved on to the full-scale breadboarding phase, and here you can see our design for the full-scale breadboard. And the thing to notice is that for the purposes of the Earth-based testing and to help with the aerodynamics, a flare was included on the back of the penetrator, essentially to lengthen it, because otherwise the penetrator had extremely short length to diameter ratio, thus resulting in potentially very poor aerodynamics during its flight during the full-scale testing. So we extended the length of the penetrator with this hollow flare. Now comes the most interesting bit, the full-scale impact tests. Now, these were carried out in July 2013 at the kinetic-operated Ministry of Defence test range at Pendine, Wales in the UK. And you can see in the background image a Google Maps picture of the test site, and this track was 1.5 kilometers long, and it's made up essentially of rails with rocket sleds on the rails, one carrying the penetrator, one carrying solid rockets, which powers the sleds down the rails, achieving, in our case, 300 meters per second impact velocity. We had 2 firings done, one out onto an ice target, which to simulate Europa, and one into a sand target to simulate impact on Mars. And the target dimensions were 2 by 2 by 2.5 meters. Our first big challenge on the site was to prepare the ice target, and by our ironic bad luck, despite being in Wales, which is not famed for its fine weather, we found ourselves on a 27 degrees Celsius day in July trying to build outdoors a huge block of ice and hope that it would last, in fact, overnight before we could do the test the following morning. It took about 8 hours of the day before to put together a few hundred blocks of ice sculpture, ice blocks, which are the purest form of ice blocks we could obtain. And these were stacked into a target of 2 by 2 by 2.5 meters, surrounded by huge concrete blocks and covered by steel bars, all designed not only for insulating the ice, but to protect and contain the ice during the impact, so we didn't have ice shards flying at high velocity and all. Here's the penetrator all ready to go on the rocket sled. It's held down by metal bands, which would be removed prior to the penetrator being released for the impact. And behind it are the solid rockets, which you'll see in the next slide. Here's a top view from behind of the penetrator with the 12 solid rockets on the back that we're going to accelerate it from 0 to 300 meters a second over a distance of 300 meters. For the purposes of this test, our main goal was to test the double-walled vacuum flask concept of the penetrator to show that that would still maintain thermal isolation after the impact process. But we also included components of the sampling mechanism, as well as a electrode assembly of the mass spectrometer inside the forward compartment to test the survivability of that. There were also electronics and an accelerometer to support the data logging and measurement of the G-loads during the impact process as well. Now I'm going to show you the ice impact video. Now, I must warn you, this is a very fast event, and literally, if you blink, you'll miss it. So keep those eyelids wide open, and here we go. That was quite some bang. We'll see it now in slow motion. And you'll see that the penetrator is released from the slide from the sled as the rails dip downwards, and the bands that hold it down to the sled are cut, and the penetrator goes into free flight for about 13 meters before it impacts the ice, and that's a huge amount of energy deposited into that ice, so much so that the concrete blocks and steel beams are shifted by quite a distance during that impact process. But you would have noticed how the nose of the penetrator is tipped up due to a rotation that occurs after the release, and it achieved an angle of attack of 22 degrees at impact, which was much higher than we predicted. And this was as a result of the very low length to diameter ratio, as well as the center of the penetrator not being far enough forward, and the interaction of the bow shock with the ground resulting in a proximity effect, also adding to the rotation of the penetrator itself. But this is something that is purely due to the ground effect of the aerodynamics and would not exist in real flight on an airless body. Ice was in tiny pieces like you would put into your cocktail, and we had the penetrator somewhere inside there. But all we could do was remove some of the top slabs and it by getting some shovels out. That was the best way. But fortunately, because of the way the penetrator went in at the high angle, it ended up moving upwards, and in fact, as we found out later, it had collided with the top stainless steel bar and ended up pretty. Here's the penetrator as it looked after we got it out. As you can see, it's relatively undamaged, apart from some of the paint. The blue paint had been shaved off on the tip during the impact process. Here you can see a trace of the g-forces that was measured by the acceleration that was measured by the accelerometer on board, and on the bottom axis is milliseconds, and on the left axis is thousands of g's. So on the first impact with the ice phase, we measured a g load of 15 kilog's, and what we didn't intend was what you see as the second, even higher peak, almost at 20,000 g's, and that was the impact of the penetrator with the steel bar. And what happened, as I said, was the penetrator curved in its path up through the ice and ended up much higher than expected, and it actually collided with the steel bar and received a steel against steel impact, which turned out to be even higher than the steel against ice. We opened up the penetrator, we disassembled it after the impact, and taking off the front bay where the compartment of the component of the mass spectrometer was, which was packed within glass beads rather than with solid potting compounds, so that we could easily remove it, we found that the component was largely intact, and even the 3mm sapphire beads, which held off these electrodes from each other, survived the 15,000 and then 20,000 kg impact, which was quite remarkable, and showed that essentially there were designs that could be made for even scientific instrumentation as sensitive as this to be able to survive such G loads. The other thing that we tested was the sampling mechanism, and this largely survived, except for one of the motors showed that the rear housing was removed during the impact event. But this is not considered very critical, and we believe that there are workarounds to solve this problem in the future. In addition to this, we did test the penetrator inside a thermal chamber after the ice impact event to show that the thermal properties of the penetrator, and especially the vacuum isolation, was still maintained despite the severe environment that it had suffered. And this would be critical in the mission, and our test showed that indeed the thermal isolation was still as good as it was prior to the impact event. And so the whole concept of using a double wall penetrator with these plastic standoffs actually survived and was proven to work. And that was an excellent result for us. So now this year we've been undertaking a phase 3 development program for the penetrator to take some other subsystems that need to be developed further for high G to a higher TRL, and these include the primary battery technology that would be required, as well as a miniaturized high G UHF comms transceiver. So we are making a steady progress of individual subsystems, taking it forward, and hopefully in a few years we'll get to the point where we have got all of the critical components of a penetrator tested to high survivability, and we'll be able to show that a penetrator platform, at least, is ready to be considered. In conclusion, ESA has been undertaking a long-term penetrator technology development program now, and the shell and sampling mechanism survivability has been proven, thermal concept crucially has been validated, and further development of battery and comm system is undergoing right now. And, well, we're awaiting flight opportunities, and we look forward to the time when the penetrators can seriously be considered in future mission design and one day hopefully see them fly successfully in space.